Welcome back. We are now going to talk about estimation of state when the state is changing in time according to a pre-specified dynamics. As we always do, we first want to have a handle when the dynamics is a linear dynamics. So let me talk about the classification of problems to see where we are. So the key players are model, observation. Model can be deterministic, stochastic. Model can also be linear and nonlinear. And model can be static and dynamic. Likewise, observation. So when I say observation, please remember, this is the picture you have to have at the back of your mind. This is the model space. This is the observation space. Observation lie in here. Generally, we assume this is Rm. We assume this is Rn. X. I always want to be able to connect this. When this is H, or this can be H. So when Z is equal to H of X, when Z is equal to H of X plus V, so without V, it is deterministic. This is linear, noisy, nonlinear, noisy. In this case, H is a matrix of size m by n. In this case, H is a function which is m by 1. This H as a function we already talked about. H of X is H1 of X, H2 of X, and Hm of X. So what is this? I want you to look at this like this now. H, here is X, this is H of X. H is called the forward operator in the context of meteorology for whatever reason. So it takes a vector input, it gives a vector output. So this is called vector valued functions of vector. We have already seen scalar valued function of a vector. We have already seen scalar valued function of a scalar. So in data assimilation, we have to deal with three types of function. Scalar valued function of a scalar valued function of a vector valued function of a vector. So in the nonlinear case, that's what's given. So these are the primary classification. So we talked about static, linear, deterministic. We talked about static, linear, stochastic. We did not indulge into nonlinear system for static problem. Now we are going to go for dynamic, linear, deterministic, where the observation is going to be noisy. Do you see the combination, please? The choice of model, the choice of observation, the combination of the two. Static, dynamic, linear, nonlinear, deterministic, stochastic. So now I'm going to talk about deterministic, linear, dynamic model. I'm also going to talk about linear and stochastic observation. Stochastic observation. So that's a choice. And what is the resulting technique? The resulting technique go by different names. Variational method. It's also called 4D VAR. Variational method is more from mathematical perspective. 4D VAR. Meteorologists cannot use the same terminology as the mathematicians use. Why? because they want to look different. Why is this called 4D-VAR? The meteorological field variables have 3 spatial and 1 temporal. So the problems lie in this 4-dimensional space, and it's a variational approach. So they have variational but added a descriptor 4D-VAR. So 4D-VAR refers to 4-dimensional variational assimilation methods. And what are the other terminologies? Adjoint method. Sometimes is also called first order adjoint method. First order adjoint method. First order adjoint method. So these are all the names by which it is known. So I'm going to first describe the model, describe the observation, and then talk about the problem. So the model. The model is xk plus 1 is equal to m times xk. Xk is a function of Rn. M is a m by m matrix. N by n matrix. X naught is the initial condition. Initial condition. So if I run the model forward in time, I will generate the sequence of states. So this is called the trajectory of the model. Model trajectory starting from the initial condition. The solution for this equation can be written as x of k. In general, x of k is a function of x naught and k. The solution depends on the initial condition and time. And if the model is given like this, let's write that model now. X1 is equal to m of x naught. X2 is equal to m of x1, which is equal to m times m of x naught, which is m square x naught. From here, you can easily see xk is m to the power of k x naught. Are you with me? You just keep iterating it. All of you? I can compute the solution xk for any k by m to the power of k x naught. What is m to the power of k? M to the power of k is the kth power of a matrix. Now there are rules and regulations. In numerical linear algebra, there are very hard and fast rules. Never compute the product of matrices unless that is what you want. Never compute the inverse of a matrix explicitly unless that is what you want. But here we are not doing numerical computation, we are doing theoretical analysis. So I can afford to use metric product, powers, inverse to be able to bring out the underlying concept. But when you are trying to do numerically, never multiply matrix by another matrix unless that is exactly what you want. Avoid matrix multiplication. Avoid computing the inverse of matrices explicitly. These are the golden rules in numerical linear algebra. Because why? They are very time consuming. They are very time consuming. Don't spend your money if you don't know, if you don't want the results resulting from that computation. You have to be lean and mean. The computation scheme has to be lean and mean. Are you with me? Good. So what is the statement of the, then I have observation. So the model runs. The model is supposed to capture a physical phenomenon. I'm assuming my model is faithful to the physical phenomenon. I can observe the phenomenon. I can compute the observation, which are functions of the state, plus V. I can assume this is Vk, the noise changes in time. But I will also assume Vk is normal with fixed distribution, standard normal with mean zero and covariance R. When R is identity, it becomes standard normal. When R is different from identity, it is normal with the covariance matrix R. So what is the statement of the problem? We don't know x naught. So x naught not known. But whatever x naught is, I can compute the solution. So here, look at that, xk is a solution. So what does it mean? I am given a bunch of observations. So the problem is x naught is known. My job is to be able to estimate x naught. But what is given to you? Given to you is a collection of observation at time t z1, z2, z capital N. So given a collection of observation starting from time 1, 2, 3, n, I would like to be able to estimate x naught where z's are related to xk and xk evolves according to the model. So xk has information about x naught. Z has information about x. Are you all with me, please? So Z has indirectly contains information about x naught. I'm given a bunch of n observation in continuous time. In practice, the theory will work. Even if I don't get in continuously, I can have it at time 1, at time 5, at time 7, at time 11, at time 15. The interval where the observations are going to be observed need not be uniform. But then the indexing becomes a little tricky. So we are going to, without loss of generality, assume I'm going to have observation in the first n instances of the clock time, the model clock. So what is the model clock time? Xk plus 1 to xk. So that is a one step. So this is called one-step transition. One-step transition. You remember we talked about forecast, XB. That forecast, XB, could be the model forecast. All of you may? That's right. That's right. Do all of us understand the problem now? I have a dynamic model. The model evolves in time. I didn't know where it started. I have a mathematical way of characterizing the model state as a function of the unknown initial state. I want to be able to capture information about the model state every time k. To that, I fall back on observation. The observation contains linear information about the model state, but it is noisy. But I do know the noise covariance. So given z1, z2, zn, my job is to be able to evaluate x naught. Zi contains information about xi, and xi contains information about x naught. So from z to x naught. You see the link, please? How many of you with me? You all have aha on the statement of the problem? How many of you with me? Raise your hands, please. That's right. The problem statement must be clear to you. When there is no dynamics, x naught is x, and that's the problem we solved. Are you with me? That's right. Yesterday morning, we solved the problem. That's a static problem. There is no dynamics. Initial condition x naught is the unknown. I observed. The observation contains information about that unknown state x. Instead of calling x naught, I call it x. We did the estimation technique. Sometimes this is also called retrieval. Retrieve the initial condition from the information given through the observation. All of you? So what's the next step? Build a cost function. Why? Every estimation problem, I want the estimate to be best in some sense. We don't want to do anything which is not the best for the given circumstance. So we are always seeking an optimal estimate. Optimal in what sense? That depends on the way you formulate the problem. You can formulate the problem in a Bayesian framework. You can formulate the problem in a least square framework. You can formulate the problem in what's called maximum likelihood method of estimation. So estimation theory, which is part of mathematical statistics, is one of the very well developed branches in statistics. All of you, may please? Hey, that's the reason I tell you, you have to get a good book on mathematical statistics. The book I would suggest is Linear Statistical Inference by Dr. C.R. Rao. It's available in Indian edition. It's a classic book. It's a classic book. C. Radhakrishna Rao. He lived up to almost 100 years. He passed away very recently. He worked in India until he retired at the age of 60. After 60, he went to the United States. He worked for 40 more years. He almost died on the job. Aruzme, you speak of accomplishment, you speak of scholarship, you speak of contributions. He's a model for almost all of us. So please ask our library to buy. Please buy a copy of the book Linear Inferential Statistics by C.R. Rao. It's a great source book on matrix theory, optimization theory, and statistical analysis. All of you? Good. So there are various methods of estimation. I have an estimation problem. I can formulate this problem in any one of the different estimation techniques available. I want to have a continuity in the methodology I speak in this class. I have chosen least squares method. For the sake of continuity, so you can see the static problem is a special case of the dynamic problem. Dynamic problem is an extension of the static problem, and all those interrelations you can see. All of it, me? Good. So for every, so let's go back to our famous diagram all the time. This is the model space. This is the observation space. This is Rn. This is Rm. So xk evolves around here. Zk evolves around here. Xk and Zk are related by H. Are you with me? So Zk evolves. Zk contains information about Xk. And Xk evolved from X0. So this is the guy everything started from. I got here after running through the model k times. Everybody? So he contains information about this, and this information is contained in here. So from here to here to here. From here to here, I use H. From here to here, I use the model. All of you? It is trying to squeeze the information contained in the observation about the unknown. And how do you squeeze it? And that's the estimation procedure. All of you? Good. So whenever xk, zk comes in, there has to be a forecast error. So what does it say? The model says at time k, the state is xk. The observation is zk. Now I'm going to introduce what's called the model predicted observation. Model predicted obs. What is that? This is zkm, which is equal to h of xk. So if xk is the state of the model, h converts the state into observation. So if I use the model to predict the observation, the model predicted or model counterpart of the observation is h of xk. The actual observation is zk. So the forecast error, ek, is equal to zk minus h of xk. Do you see this is our old friend? Z minus h of x. There is no business for k there. Why? Everything is dynamic. Everything was static. Here everything is dynamic. Are you all with me now? Am I aligning myself into the beaten track I have developed for the 3D war problem already? That's right. Hey, there's a famous proverb, I'm going to quote it. If hammer is the tool you have, every job looks like a nail. I want you to write this down. If hammer is the only tool you have, every job looks like a nail. Why? What is that you can do with the hammer? You can hit. So, in order to be able to do many things, you need a toolbox with a rich set of tools. Are you with me? But here, the tool I'm going to use is the least square tool. I have already told you how that tool works already. Are you with me? So I'm going to build on our past experience in using least squares to estimate. Fair enough? There are other ways of doing business. You should not worry about every method. You should be able to do at least by one way before we talk about what is the other way. All of it, please. Yes, you need to have a very solid understanding of at least one method before you start working about what if I use another method. So using another method doesn't make sense until you have well grounded at least on one method. All of you? And what is the grounding we have? Least squares. So what does that least squares tell you? Well, the error is a vector. The vector has multiple components. Each of them could be positive or negative. I'm going to have to build a scalar out of that vector. Sum of squared errors, weighted sum of squared errors. So my J, so let's look at this now. So EK transpose R inverse EK is the weighted sum of squared errors at time K. How many of you with me? That's right. But I have K running from 1 to N. And this I can write as summation K is equal to 1 to N. What is EK? Let me put that EK now. EK is Ck minus h of k. So this is equal to Zk minus h of xk transpose R inverse Zk minus h of xk. So Zk's are known, H is known, R is known. Xk, I can compute through the model. M is known. Are you with me? But X0 is not known. So how can I rewrite this? From here, it comes in here. Summation k is equal to 1 to n, Zk minus h of, okay, now what is xk? I already have xk is equal to m to the power of kx0. Because the model is linear, I can solve the linear system by iterating. If it is a nonlinear model, I can't do this easily. So you have to do an easy problem first, get a handle, and then go for the more challenging problems. All of you? So this is going to be m to the power k x0 R inverse transpose Zk minus h of m to the power of k x0. M is known, H is known, Z is known. Who is the only person not known? X0. So what am I going to call this? This is J of X0. This is J of X0. All of you? So if I have deterministic observation, if I did not know the error covariance, I will drop the R inverse term. With me? Now, what's Kalman filter? In a Kalman filter, we are going to add a noise to the model. This becomes a stochastic model. So linear stochastic model, where the observations are also stochastic. Are you with me? How do we estimate the state? State estimation problem is what Kalman did. He solved the problem in 1960. He solved the problem in 1960. So we are not going to take the same approach Kalman did, because his problem is different from here the model is deterministic, observations are noisy. I have a collection of n observation continuous time. With me? The initial state of the model is not known. I would like to be able to estimate the initial state. So what is the statement of the problem? The statement of the problem is minimize J of x naught, where x naught belongs to Rn. Is an unconstrained minimization problem. With me? Around yesterday, at this time, we were talking about the static problem, the same version. Now we are talking about its analog in the dynamic version. With me? So what are the steps from ANOVA? Okay, problem formulation is over. Applied mathematics takes over. Because we have converted the problem to one of minimization. One of minimization. This is a quadratic minimization problem. Why this is a quadratic minimization problem? Because each individual term are quadratic functions. Oh, I forgot to put an xk here. Xk here, that's right. Okay, so there are a couple of nuances I want to talk about. Here I'm assuming m, the model, doesn't change in time. If the model variable itself changes in time, are you with me? Yeah, I have assumed my observation h is invariant in time. That could change in time. Are you with me? So the model is a linear time invariant model. Time invariant means what? The model matrix does not change in time. Linear time varying, linear time invariant. Observation, time invariant operator h, time varying operator h. So I can complicate it by making m to mk, h to hk. The complications are not too difficult. The same methodology can be applied. But to make it simple, I'm assuming m remains constant, which is true in most of the cases. Are you with me? My observation system, my observation network is fixed. It doesn't change. My model is fixed. It doesn't change. Are you with me? So you have to argue why you have to consider the model changing in time. You have to argue why the observation network happened to change in time. So there are lots of variations of the theme. I'm talking about the simplest possible case. Time invariant model, time invariant observation operator. M is constant, H is constant, X naught is constant but unknown. I'm given a bunch of observation, noisy. I also know the properties, the second order properties of the observation noise. Second order property means what? Knowing the mean of the covariance. Knowing the mean of the covariance. So what is the next step? The next step is compute J of x naught equated to 0 and use the gradient. If you equate to 0, you will get a linear equation. Either you can solve the linear equation for the optimal state, or even you don't have to, then you compute the gradient and use it in a sequential minimization technique such as gradient technique to be able to move towards the minimum. And we have talked about all those things earlier. With me? Whichever way you do, I have to compute the gradient. So computing the gradient is a little tricky. And that's where the notion of a joint model comes in. That's where the notion of a joint model comes in. So before I introduce the notion of a joint model, I'm going to calculate the expression for the gradient of this objective function. All of you? That's right. So what is the objective function? He is the guy I need to handle. All of you? Here there are two terms. Here there are two terms. If you multiply, there will be 4 terms. One product is zk, R inverse zk, that is independent of x naught. Zk transpose R inverse this, that depends on x naught. And zk depends on x naught. This depends on x naught quadratically. So there will be one quadratic term, 2 linear terms, 1 constant term for each k. All of you with me? I have to compute this, I have to add them up. compute this, I have to add them. The expression may look different, but the principle we have already seen. So what is the basic principle we are going to use repeatedly again and again? If A is a vector Rn, if X is a vector in Rn, if f of x is equal to A transpose X, the gradient of F with respect to X is A. That's the first rule of the multivariate calculus. If X belongs to N, if A belongs to N by N, and A is symmetric, and assuming SPD, for the sake of our problem, if you consider f of x is equal to X transpose AX, the gradient of F is equal to 2AX. These are the two rules from multivariate calculus we have used repeatedly. How many times? About at least 3 times by now. Are you with me? That's right. The same rule has to be applied. The same rule has to be applied. To do that, let me try to expand this. Expand k is equal to 1 to n. For the sake of discussion, I want to write this down. Zk transpose R inverse Zk minus 2 times. You already know where the 2 comes from, right? There are 2 linear terms, like they are essentially the same, I can combine them. So 2 times Zk transpose R inverse, Zk transpose R inverse, H m to the power of k x naught. Please look at that. The coefficient of x naught getting more and more complex as we go from unweighted to weighted to dynamic. Plus x naught transpose, and what is the matrix here? I have to multiply this with this. That becomes H transpose, that becomes mk transpose, H transpose, R inverse, H m to the power of k, x naught. You can multiply this term with this. Please remember that's a transpose. So x naught transpose, mk transpose, x naught transpose, mk transpose, H transpose, R inverse of that. But from matrix theory, you should know mk transpose is equal to m transpose to the power k. The power of the transpose is the transpose of the power. All of it me? R is a symmetric matrix, covariance matrix. M need not be. The model matrix M is simply a square matrix. It need not be symmetric. So what is the one thing we want to assume? The model matrix is non-singular. The determinant of M is not 0. I'm going to make that basic assumption. Why? If the determinant of M is 0, means the columns of the matrix are linearly dependent. If the columns of M are linearly dependent, that's a defect. For the model to be non-defective, the matrix of the model must be non-singular. Just like the matrix H we talked about yesterday, the columns of H must be linearly independent for the problem to be well posed. All of it me? Same ideas carry over. So here, what are the assumptions here? The model is a full rank matrix. My H is a full rank matrix. So the rank of H is equal to the minimum of M and N. I'm going to assume all good things in life. Why? I want the problem to be well formulated. I want the problem to be well formulated. What if the columns of M are linearly dependent? Then the model does not have the degrees of freedom, because one column depends on some of the other columns. Are you with me? I want the model to have the full-blown freedom. So that's natural. We have already seen the reason for H to be a full rank matrix in the last class, for the problem to be well formed. All of you? So these are the tests you have to make before you jump into doing data assimilation problem. Is the model well defined? Is H is well defined? Is the model is well posed? This problem is not a well-posed problem if M is not non-singular, if H is not of full rank. All of you? That's right. That's right. So let's try to compute the gradient of this. Now you see the power of what we did yesterday. Yesterday it was looking more like an applied mathematics class. Vector space. Are you with me? Linear algebra, multivariate calculus, and so on and so forth. And when we started doing the estimation of the unknown parameter in the static deterministic problem, we saw how all the tools came to fruition. Are you with me? And that experience, we are carrying it over. That's the reason we did what we did. All of you? That's right. So, what is this? This is going to be summation k is equal to 1 to n. Please remember, the gradient of the sum is the sum of the gradients. Are you with me? Come on, guys. D by dx of f plus g is equal to df by dx plus dg by dx. So the differential coefficient of the sum is the sum of the differential coefficient. Same thing carries over to here. So according to that law, so that means my gradient operator and the summation operator, they commute. You remember? We talked about that commutativity in the last class. So this is 0. The gradient of this is 0. The gradient of this, let's look at this now. I have to rewrite this in this form, A transpose X. Instead of X, this is X naught. Everybody? So if I equated this to A transpose, this becomes A transpose X naught. Its gradient will be 2 times A. Minus 2 times A. So if this is A transpose, what is A? The transpose of this. Come on, guys. We are not doing it for the second, they are doing it for the third time. This becomes like this because I know how to compute the derivative. So this must be a row vector. Let's check that. Z is a column vector, Z transpose is a row vector. A row vector times the matrix times the matrix times the matrix. That's a row vector. That row vector, I'm going to call it A transpose. Hello? I'm looking at people who are nodding the right way. Raise your hands, please, if you're with me. That's right. So if I can rewrite this as 2 times A transpose X naught, what is the gradient with respect to X naught? A. Where does it come from? It comes from here. So if A transpose is this, what is A? The transpose of that. Transpose of the product is the product of the transposes taken in the reverse order. That's right. So this is going to be MK transpose, H transpose. Now, what is R inverse transpose? R is symmetric. R inverse, R is symmetric and positive definite. R inverse is symmetric and positive definite. So if R is symmetric and positive definite, R inverse is also symmetric and positive definite. These are all theorems in linear algebra. Please mark your margin. I need to know to prove this. Come on, guys, that's how you build your knowledge. This is the second time we are doing this morning. That's right. So the transpose doesn't affect R inverse because it's symmetric, and the transpose of a transpose is itself, that is ZK. Wow, I got through. Now, what is this? That looks like this. So this is the matrix A. This looks like X transpose AX. This is 2AX. And A is that, so this is simply 2 times MK transpose, H transpose, R inverse, H MK times X naught. All of you with me? So I have to compute the sum. Okay, now I will tell you, sometimes we stick in a half here. I already talked to you. If you multiply a function by a positive constant, the function varies, but the location where the minimum occurs does not. And why do I sometimes multiply by half? There's a 2 coming in, right? If there's a half, the annoying 2 will go back. If I equate it to 0, then the 2 will get cancelled. I'm not going to equate to 0. I want to get an expression for the derivative itself. That's the difference. Are you all with me now? That's right. So let us stick in a half. Let us stick in a half. The 2 gets cancelled. Everybody? Nobody should have a problem in algebra. Should you? That's right. But algebra is a little treacherous. But you have to be careful. Good. So I can now say this to be summation. There are only 2 terms. There are only 2 terms. So summation of A plus B, AI plus BI is summation of AI and summation of BI. So I'm going to the minus M transpose to the power K. Please remember that. I'm going to apply this rule. M transpose to the power K. H transpose R inverse ZK. There is a minus sign associated with it. K is equal to 1 to N plus summation K is equal to 1 to N. This matrix, what is that? M to the power K, M transpose to the power K, H transpose, R inverse, H, M to the power K, this whole thing, X naught. Please understand, I'm not trying to equate it to 0. I want to be able to compute the gradient itself. We'll talk about equating the gradient to 0 a little later, but let's compute the actual value of the gradient. Is the arithmetic clear to all of you? Is the matrix algebra? Now you need to know how fast you should be in matrix algebra. That comes by training. That comes by training. With me? Can I erase part of this black, this part of the board? Good. So let's do that. So let's look at this now. The coefficient of x naught is this sum. Are you all with me? This is another term. So I'm going to take the negative sign here and rearrange this in a nicer way. So this can be written as, so x naught with respect to x naught is equal to summation k is equal to 1 to n. Let's look at some of the common terms. M t to the power k, M t to the power k, H transpose, R inverse, ZK, H times M to the power k x naught. Everybody believes? So these terms are common. So I can take the common factor out, which is M to the power k, H transpose, R inverse. Okay, let me take the minus sign out here. So this is going to be ZK minus H M to the power k x naught. Please check that. But M to the power xk, that is xk. Are you with me? So this is zk minus h of xk, that is ek. Are you with me? All of you with me? I'm going to give an interpretation, a physical interpretation to the expression for the gradient. So I have a model space, I have an observation space. Okay, now xk remains here, zk remains here. H of m transpose x naught, that is a state in here, which is xk, right? Everybody plays. So this difference is a m vector. This is the m vector. So this ek lies in the observation space. All of you may? You need to know which animal resides where. There are too many animals here. xk is an animal, zk is an animal, ek is an animal. Each animal has their own kingdom. Each one resides in their own spaces. Are you with me? So I want to give a meaning to this expression. So how can I give meaning to this expression? This expression can also be rewritten as minus k is equal to 1 to n, m k to the power k, h transpose r inverse ek. This r inverse ek, I'm going to call it f of k. Therefore, I can rewrite this as summation k is equal to 1 to n, m transpose f of k. I'm going to give a specific meaning for each of these things, but let's do it algebraically like this. Now, do all of us agree that this expression comes from there? I simplified this expression using this to go from here to here. From this expression, I got from here to there. So this is the simplest form in which I can look at my gradient. If I equate the gradient to 0, I will use this form. If I want to be able to compute the value of the gradient itself, I will use this form. So let's do the first form. If I equated the gradient to 0, so let us do one of two analysis. Equate the gradient to 0. So if I equate the gradient to 0, what happens? Summation m transpose to the power k, h transpose r inverse h m to the power k times x naught must be equal to summation k is equal to 1 to n of m transpose to the power k r inverse h transpose r inverse, h transpose r inverse z. Okay. Do all of us see that, please? If I equated this expression to 0, this is what I get. So this is the matrix. This is the vector. So x naught, the estimate of this, inverse of this matrix multiplying that matrix. But let's see what this matrix is. I want all of you to be very careful why I did not choose to equate it to 0, because of the following difficulty. I first need to compute H transpose. I need to multiply H transpose with R inverse. I need to multiply the product with H. Then I need to compute m to the power of k from m to the power of k transpose. By the time I end up calculating this, I'm bankrupt. I have spent all my money in computing that matrix. Now I have to borrow money to compute this. Then I have to solve the resulting linear system, ax is equal to b, ax naught is equal to b. Solving this system by Cholesky method is another going to be bank breaker. Are you with me? So even though I know how to do, it will break your bank. So we shall not do that. Are you all with me? How many of you with me? That's right. Why did we do it there? There also I did not want to multiply matrices. I don't want to compute the inverse. I want to get into the mathematical thought processes. That's why we did what we did. Please remember the golden rule in numerical analysis, numerical linear algebra. Never multiply matrix with a matrix. Never compute the inverse unless that is what you want. You are interested in the solution, not the inverse. Inverse is only a mathematical way of expressing the solution. Are you all with me? That's important. So, it is not that I don't know how to equate the derivative to zero. I can, but this leads to a path which is impossible. It's possible in terms, but it will bankrupt you. It takes a lot of time. It makes no sense to spend that much time. So what's the alternative? I want to be able to compute the exact expression for the gradient. You remember the hill climbing method I talked about? In the case of maximization, you follow the gradient. In the case of minimization, you follow the negative of the gradient. To go towards the minimum, you have a current base station, compute the negative of the gradient. You go certain step along the gradient, come to the new base station. So what is the iterative algorithm? We already know that. The gradient algorithm we talked about in the last class. So optimal solution can be computed one of two ways. One, by solving the normal equation. That's the normal equation. But in this case, computing the matrix for the normal equation, computing the right-hand side of the normal equation is so expensive, you should shun it. You should not even think about it. So what is the preferred method for minimization? Sequential minimization. One easy method for sequential minimization is gradient method. Please remember, in this class, in this course, we are not covering optimization techniques. All of you? How many of you know how gradient method works? How many of you have heard of gradient method? Everybody has gradient method. Everybody knows have heard of gradient method. You know how it works. Please understand, the bare minimum in optimization technique you need to know is gradient method. If you don't know gradient method, don't tell anybody you know gradient optimization. That's the bottom line. Are you with me? You should know what the method is. You should know why it works. When it will work, when it won't work. What are the modifications of gradient methods? Are you with me? That's a science in itself. All of you? That's right. Have you heard the story of 5 blind men looking at an elephant? You have not heard the story? 5 blind men looking at an elephant. One looks at the trunk, one looks at the leg, one looks at the tail, one looks at the ear. But the elephant is more than the union of all the descriptions that the 5 blind men describe. Are you with me? Sum is bigger than, the whole is bigger than the sum of the parts. The whole elephant is bigger than the sum of the components of the elephant. So I'm now wanting you to see that elephant. Are you with me? Come on, guys. The challenges, problems in data assimilation. What are the various things you need to do, and so on and so forth. So resorting to Cholesky method is a no-no. It's dead on arrival. So what is it I need to do? I need to resort to sequential optimization. Sequential optimization means I need to compute the exact value of the gradient. The exact value of the gradient I have computed here. Look at this. Even here, I missed mt to the power k. Sorry. I missed the k. Sorry. This is mt to the power k. This is fk. The whole thing is fk. Everybody? How many of you with me? ek, fk, mt to the power k. Mt to the power k involves matrix multiplication. So what is it I now need to do? I need to compute the gradient without doing matrix multiplication. What is the answer? Adjoint method. So what is adjoint method? Adjoint method is a mathematical way of computing the value of the gradient in the context of dynamic data assimilation problem where you don't compute matrix-matrix product. It's a clever way of avoiding matrix-matrix product, yet computing the solution. Are you all with me? You all have an aha here? Come on, guys. That's right. Your silence is often deafening. You need to be a little bit more louder. Wow, aha, I got it. You have to enjoy the moment. All of it, me? So what is the last step? The last step is to get a good algorithmic way to compute the gradient while not doing matrix-matrix multiplication. But before I do that, I want to explain some of the terms in here to give some physical meaning to it. Please understand, this is only for a linear system. For a nonlinear system, there is another level of complexity involved. So I will write the expression for Jx naught. So this form is not useful. We have already seen equating to 0. This form is the same as this form, except that I'm combining the whole thing, calling it Ek. Everybody? And this form reduces to this if I combine Ek with this. So before I go further, let's explain that term. So this is the model space. This is the observation space. We have already argued Ek lives in the observation space. With me? So what is f of k? F of k is H transpose R inverse Ek. Sorry, let me put it f of k. Please understand the notation. I think I want you to be thoughtful about this. If I have a f, I can put it in the feet, that's called subscript. I can put it in the head, that's called superscript. I can put it in the stomach, that's called the functional notation. All of it may? That's right. Subscript, superscript, functional notation. So there are various ways of using all these three places to the advantage of notations. We already know how to use many of them. I simply want you to look at them now. Ek divided by, multiplied by R inverse, what is that? So this is the forecast error. This is normalized forecast error. So R inverse Ek also lives here. But H goes from here to here, H transpose goes from here to there. Therefore, f of k, which is equal to H transpose R inverse E of k, what is that? That is the model space counterpart of the normalized forecast error. Please understand, I am bringing everything to the model space. H takes you from model space to observation space. H transpose takes you from observation space to the model space. As you have been, some of you observed, there's also an equivalent observation space formulation. You cannot worry about everything all the time. You have to know one at a time. So I'm trying to confine myself to the model space formulation in all my analysis. Therefore, when I say this is equal to m transpose to the power k f of k, what is this? This is the linear combinations of the model space counterpart of the normalized forecast error viewed from the model space. Hey, that is the explanation for this. And everybody, so if I wrote this, mt f1, mt square f of 2 plus mt to the power n f of n. All of you? Did you all get that? Come on, guys. Please nod your head one way or the other. Yeah, go ahead. Huh?
Minus sign.
That's right, minus sign. That's correct. Stick in there. So instead of putting minus sign here, I will put a minus sign here. I'm computing the negative again. With me? Good. Thank you. But he's my compiler today. Thank you. Thank you. Where the minus sign coming from is here. He's very careful. Thank you. Thank you. Now, do you understand the meaning of EK? You understand the meaning of FFK? Good. Now, I'm going to go to algebra. In algebra, there is, how many of you know how to evaluate polynomials in the most efficient way? There's a method called Horner's method. You remember, have you heard of that? Come on, guys, where did you go to school? When did you evaluate a polynomial in your life last time? How come any one of you did not raise your hand for Horner's method? I'm not criticizing you guys. That's a simple technique in polynomial evaluation. Are you with me? Now, do you understand this is a polynomial in matrix? Where f's are the coefficients? So it looks like a polynomial in a matrix. So if I know how to compute polynomials efficiently in the scalar case, I can borrow ideas from there to compute polynomials in the matrix case. That's the idea. So let me talk about Horner's method for so ax cube plus bx square plus cx plus d. What is one naive way of doing? Compute x square, x cube, then multiply x cube by a, x square by b, c by x, d by x. You compute the total amount of multiplications you need to do. Now, I'm going to suggest the following. Ax plus b times the x plus c times x plus d. That's that. All of you? Ax plus b, then that becomes the coefficient of that by c, that becomes the coefficient of that plus d. This method is called Horner's method. What is the beauty of this method? You cannot, okay, now compute the number of multiplications addition for this method. You compute the number of multiplications additions for any other method. Horner's method has the least number of operation in computing the values of the polynomial. It's not the best method. All of you? This method enables itself for writing a program very easily. So what's the homework for you? Write a program to evaluate a polynomial using Horner's method. Write a do loop to do that. So homework problem. Hey, you don't want to start writing an agile code to start with. You have to build slowly, right? So test your understanding of programming by writing a simple program to evaluate a polynomial by Horner's method. Okay, so given that, what are we going to do? We are going to do the following. So I'm now going to introduce a new terminology. So how to compute this? I'm computing this. So this is equal to f of n. Equal to f of n. Okay, I'm going to start a new iterative process. F of n. So lambda n minus 1 is equal to m transpose f of n minus m transpose f of n minus 1 lambda n f of transpose. Okay, maybe I'll write this down and then go from there. Sure, that may be even better. Transpose f of n plus f of n minus 1 And then lambda n minus 2 is equal to m transpose lambda n minus 1 plus f of n minus 2. And continue this way. Lambda 1 minus lambda 1 is equal to minus of, please understand, you compute lambda 1 according to this, and the gradient of jx naught is equal to minus lambda 1, because the negative sign comes in, right? All of you? Now, do you see this equation? Hey, I want you to look at this now. So what is, let's compute the values of this equation. So what is this one? This is equal to m transpose f of n plus f of n minus 1. What is this going to be? M transpose times, so I have to substitute this value here. I have to multiply this by m transpose. So this is equal to m transpose square f of n plus m transpose f of n minus 1 plus f of n minus 2. All of you with me? How many of you with me? Does it look like this? How many of you have an aha? Those who did not have an aha, where did you miss me? You remember in Christian wedding they say this? If you have any objection to these two people getting together, you shall object now or shall remain silent forever. Now here you can ask a question any time. But I want you to think about it and nod your head. Look at this expression. Does this look like the... So, I first multiplied f of n by mt. Then I multiplied by mt square by the f of n plus this, m of this. So you multiply once more, you multiply once more, you multiply one more, you multiply one more, you do this n times, you get this. Everybody? I'm now going to write this as a simple do loop. Lambda n is equal to f of n. Lambda n minus 1 is equal to m transpose lambda n plus f of n minus 1. Do, I should say, k minus 1 to k minus 1. Do k is equal to n minus 1 to 1. Do you get that loop, please? How many of you with me? That's a homework, and that's a program you have to write to compute this. That is exactly the same program you will write to compute this. Instead of m, you will have coefficients. Instead of f, you will have x's. But the structure of this program is exactly the same as structure of this program. What's the beauty of this? I never multiply matrix with matrix. Why? This is a vector. I compute another vector which is matrix times a vector plus a vector. And then I multiply a matrix times a vector plus a vector. Matrix times a vector plus a vector. Matrix times a vector is much cheaper than matrix times matrix. So this is called the backward dynamics. It's also called adjoint dynamics. Why this is called adjoint? This is the adjoint of the model dynamics, which is xk is equal to m of xk. Xk plus 1 is equal to m of xk. So the model moves forward in time. The adjoint moves backward in time. Backward in time. Are you with me? The transpose, so what is a transpose? Transpose has a property that's called adjoint of a matrix. So what is the property of the transpose? I'll come back to that. Before I go, I don't want to tell too many things. Now, are you all with me? I want to go back to once more. Are all with me on this expression? So what is adjoint method? Adjoint method is a clever way of computing this expression while avoiding matrix computation. By recognizing this to be equivalent to evaluating a polynomial, I can apply Carnot's method. That suggests that this computation can be rewritten like this. This computation can be encapsulated in one single do loop, where the do loop starts at n going backward. The model for going forward in time, the adjoint method coming backward in time. By computing the model solution forward, by computing the adjoint solution backward, coming back to the time 1, you get the gradient. How many of you are with me? How many of you have heard of adjoint method earlier? How many of you know it now? Come on, guys, please. Now I'm going to give you a practical algorithm that they use to implement this when they say, I have a 40-var algorithm to do data simulation. You all have an aha? Come on, guys, you all look tired. I know, sitting around is more difficult than standing and talking. I know your difficulty. Are you with me? That's right. But the point is, we cannot let the ahas go by. So let me hear the ahas once more. Aha. Good. You are not going to say aha just to satisfy me. Satisfy yourself. You should be your own critic. So who must be your best critic? Self. All of you? That's right. So what is the homework for you? The homework for you is to realize that this can be written like this. Once you realize this can be written like this, you can encapsulate it in a program. This program is no different from the program for polynomial evaluation. And you remember, model goes forward in time, this comes backward in time. Good. Now I'm going to summarize the whole thing in the form of a beautiful diagram to tell the essence of how adjoint codes are made. Why it is called adjoint, we will talk about it probably this afternoon during the discussion hour. That will be useful. So I am starting at x naught. I run the model forward in time. I have x1, x2, xk, xn. I get zn, I get zk, I get z2, I get z1. I have h of xn, I have h of xk, I have h of x2, I have h of x1. So I have en, I have ek, I have e2, I have e1. Ek is equal to zk minus h of xk. You all know that, right? So run the model forward in time. You have x's. Compute the model counterpart of the observation. These are the actual observation. Subtract the actual observation from the model counterpart of the observation, compute the error. All of it with me? Everybody? Then compute f of n, f of k, f of 2, f of 1. And you know the relation between f of k and e of k. F of k is equal to, f of k is equal to, I don't want to make a mistake, H transpose on inverse ek. With me? All of you? Once you have f of n, what do you do? You start going backward. Lambda n, lambda k, lambda 2, lambda 1. Everybody? And you get that job. You get the gradient. So you have to run the model forward in time. You have to run the adjoint backward in time. The adjoint model and the original model, they are essentially the same model except for the transpose. Computationally, going forward, coming backward, essentially the same time. But you have to do this loop, get the gradient. Then what is that you do? You want to get x naught nu is equal to x naught minus alpha times gradient of j x naught. So you compute the nu. Then start the model from new, go, come back. Compute another new. Go, come back, another new. All of it, me please? When do you stop? You stop when the absolute value of the gradient is less than or equal to epsilon. Epsilon could be 10 to the power of minus d. If d is 2, 2 decimals. If d is 5, 5 decimals. Everybody? That's right. As you come closer and closer to the minimum, the gradient must be shrinking in its value, right? If the gradient value has become very small, and if we have guaranteed that objective function has only one minimum, you can conclude, I have come back to the promised land. I may not be in the promised land, but I'm in a very small neighborhood. Are you with me? You can never do anything exactly computationally, especially in real arithmetic. Are you with me? Are you all with me, please? So when I say I have found the optimum, I have found the optimum to some error criteria. Wow. You all have a wow, aha? Wow. That's right. Honestly, I want an honest answer. How many of you have heard of 4D war but did not know the detail? How many of you have heard of it, now know the detail? Some people are raising the hand only halfway. I don't know why. Raise a hand. You have to raise both the hands actually. If you don't want to raise both the hands, there is some problem, you have to ask a question. Cry baby gets milk. Isn't that the proverb? I grew up in a small village. People always used proverb for anything and everything. Are you with me? I want to tell my story. Wait. In villages growing up in South India, people will always use proverbs. But the proverbs are beautiful. It's impossible to translate a proverb from one language to another language. Every language has beautiful proverbs, right? So they won't answer directly, they will tell you the proverb, you get the answer. Are you with me? So here there is no proverb. So I'm used to using proverbs. Cry baby gets milk. Why? You get the answer only when you ask a question. So if you don't ask a question, you consciously believe you have no answer, no question to ask. That means you have a total aha. Are you with me? Now your turn.
So if I compare this...
What's that?
If I compare this 4D wire with 3D wire, so now I am getting two advancement of 4D wire over 3D wire.
No, there is no question of versus. The question of versus doesn't hold water. 3D war is meant to talk about one class of problem. 4D war is for another class of problems. The problems are different. The solutions are different. Just to go back, what is the question of 4D war? 3D war? I want today's weather. I get information about today's weather from observation. I also got information from yesterday's forecast about today. Which one do I believe? I know the variances associated with the observation as well as the previous forecast. So I'm going to take the optimal combination of the two. That optimal combination is an estimation. Are you with me? So 3D war is meant to do things at a given time, given two pieces of information. 4D war is something that is a model that's running. I have observations. I want to move the model towards the observation. Please understand, that is reality. How do you get information about reality? Through observation. You have to observe reality. But reality is tough. Mother Nature doesn't give things easily to you. There is always, when you measure her, there is a noise. But I want to be able to predict. To predict, I need models. So I have to pick a model that is germane to the process in question. I want to pick a quasi-geostrophic vorticity equation if I'm interested in trying to talk about the motion of a hurricane. Are you with me? So hurricane forecasting people have to start with a model which is germane to the dynamics that explains the motion of a hurricane, which is quasi-geostrophic vorticity equation. If I want to be able to understand the cloud formation in summertime when there is humidity, heat and everything else, you have to understand what's called convective, Rayleigh-Bernard convection. That's a different class of model. So the process decides the model. The process replicates Mother Nature's behavior approximately. All models are approximate. Hurricanes in Atlantic, hurricanes in Pacific, hurricane in Indian Ocean. Indian Ocean, Arabian Ocean, Indian Ocean, we don't have too much hurricane, but Bay of Bengal. Hurricane in Sea of Sinai, hurricane in Japan. Hurricane is a hurricane, but the climatology of the hurricanes are different. Why? The central part of Atlantic is much hotter. The water in central Atlantic is much, much hotter, east of Florida. But Sea of Japan, it is not that hot. Bay of Bengal, it gets very hot. So the climatology of hurricanes are different, the models are similar. So how do you use the same model to be able to represent the hurricane in Atlantic, Pacific, Indian Ocean, and Bay of Bengal and other places, different kinds of parameterization to take the locality effect. So to be able to get a good prediction for the movement of a hurricane in Bay of Bengal, I need to observe the Bay of Bengal hurricane through radars, to satellites, by flying planes, get the data, dump it in, estimate the parameters, predict the move, then continue, good observation, continue to predict. Are you in my place? So there is a process, there is a model. The model must be appropriate for the process in question. The model has several unknowns. The solution of the model is going to become a forecast or a prediction. To be able to predict very well, I need to be able to have a good initial condition, good boundary condition, good model parameters. To be able to estimate the initial condition, the boundary conditions and parameters, I need data. So the assimilated model has a better predictive power than the model itself or the data itself. He and I go to breakfast almost at the same time. We get hungry early. So this morning he asked me a question. Can you tell me why we do data assimilation? That's the answer. An assimilated model has a better predictive power than data alone or models alone.
That we had already known about.
But that?
Why do we do data assimilation? We know that.
Then I thought that's a question. I thought that's a question you asked.
Yeah, but I want.
See, now he asked the question. Now he said, "I already know." This guy is a very difficult guy to handle.
Through the literature survey, I know that.
Okay, good.
But I want to understand this concept by using mathematics.
You got it now? He didn't answer, but he nodded his head. Come on, say it in words. Say it. No, nodding your head. You spoke. Speak now. Did you get it?
Yes.
Good. I'm safe now. I can go to breakfast very easily and talk to him tomorrow morning. That's right. I'm not kidding, but it's a good discussion to have. Are you with me now? That's right. You wanted to see the mathematics of it. You remember I told you there's a model problem for every area? The twinkle, twinkle, little star of every area. This is the twinkle, twinkle, little star for 4D war. If you don't understand this, don't worry about it. If you don't understand this, if you don't enjoy this, 4D war is not for you. I'm not trying to be crude or rude, but that's the basis. If you can't play Twinkle Twinkle Little Star, piano is not for you. Are you with me? That's right. If you can't float, swimming is not for you. That's a famous proverb, coming to the proverb. If you can't stand the heat, get out of the kitchen. Come on, guys. Do you see the thrust of that proverb? If you can't stand the heat, get out of the kitchen. So if you want to be a cook, you should be able to put up with the heat. Arithme, my proverb comes very useful very many times. Is your question answered now? You know it, but you know it mathematically too. Okay, wonderful. Thank you. Any questions, please? Yeah, go ahead. Ah.
Is it possible that the objective function could actually have more than one minima?
Ah, that's right. When can that happen? When your H function, the observation function, good question. When zk is equal to h of xk plus vk, if this is a nonlinear function, more often than not, there may be more than one minimum. Then that's not a data assimilation problem, that's an optimization problem. Are there techniques to find the global minimum in a multi-modal minimum problem? Are you with me? In other words, if I have a unimodal minimum problem, there's only one way to go. But if you have a problem where I have, so if the gradient algorithm, if I start here, I will go here. 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 Are you with me? So that is what's called exploring the space where you are going to be look for multiple minima. In general, finding the global, so that when you have more than one minima, that you have to split the concept, local minimum versus global minimum. Gradient method is capable of finding only the local minimum closest to the starting point. To be able to find the global minimum, there are variations of the gradient method by method called randomization. In that case, you may have to repeat the experiment several times until you make sure that you have covered the whole line to see whether I have caught all the minimum. So that problem is the more difficult problem. In order to avoid the difficulty, whenever possible, you concoct your cost function to have unique minimum. But even if you use the same sum of squared error criterion, when the function h is nonlinear, there's a potential for multiple minimum. In our book on data assimilation, we have given an example of a nonlinear h where there are two minimum. That's possible. That's possible. So when you are using radar data, when you are using satellite data, when you are using complex forward operator, when you say I have converged, how sure are you a converged global minimum? That's $1 million question. Are you with me? Good. Yeah. Over to you, sir.